In the grade insurance examples in the text, we've seen how adverse selection can cause certain markets for insurance to disappear. In this set of graphs here, we'll illustrate how adverse selection can create deadweight losses in the car insurance market without actually causing the insurance market to disappear. Suppose that we have two types of drivers that buy car insurance, and the market demand curve for each type is the same. In panel A, we illustrate the market demand by type 1 drivers for car insurance, and in panel B we illustrate the market demand by type 2 drivers for car insurance. In each case we assume that demand is equal to marginal willingness to pay, so we'll end up being able to measure consumer surplus along these demand curves. Type 1 drivers differ from type 2 drivers in that they are more careless on the road and therefore more likely to get into an accident. Thus, the marginal cost of providing insurance to type 1 drivers is higher than the marginal cost of providing insurance for type 2 drivers. If competitive insurance companies can identify who the type 1 drivers are and who the type 2 drivers are, they would simply treat these as different markets, and the market equilibrium price P1 would emerge in market 1, and the market equilibrium price P2 would emerge in market 2. Type 1 drivers would then buy insurance of X1, which is less than X2, the quantity bought by type 2 drivers. Type 2 drivers buy more insurance because insurance is cheaper for them. We can now overlay panels A and B in panel C with the demand curves overlapping, since we've assumed that the demand curves are the same for type 1 and type 2 drivers. Now suppose that insurance companies cannot tell the difference between type 1 and type 2 drivers, and they therefore have to charge the same price for insurance policies to both types. In equilibrium, competitive insurance companies will earn zero profit, so the single price that emerges in the market for insurance policies will end up getting insurance companies expected profits of zero. Suppose insurance companies know that there's an equal number of safe and unsafe drivers. In that case, the equilibrium price at which expected profits are zero will be P star and lie right in between P1 and P2. At that price, both type 1 and type 2 consumers buy X star insurance. Thus, anytime someone buys insurance, there's a 50% chance that the marginal cost associated with that person will be high, and a 50% chance that the cost associated with that person is low. By setting the price right in between the two marginal costs, in expectation, the price covers the marginal cost. When type 1 consumers are charged the price P star rather than P1, their consumer surplus increases by the area B plus C. But when type 2 consumers are charged P star instead of P2, their consumer surplus decreases by areas D plus E plus F. In going from separate markets where insurance companies can tell who's a safe driver and who's not, to a single market where everyone is charged P star, we therefore gain B plus C, but lose D plus E plus F. Area B is equal to area D, so those two cancel. So we get an overall change in surplus of C minus E minus F. But area C is half of area E, which means C minus E leaves us with a negative half of E, and half of E is equal to G. Thus, another way of saying that we're gaining C but losing E plus F is to say that we're losing F plus G. The deadweight loss from not being able to price insurance policies differently for the two types of drivers is therefore G plus F, and we can add some intuition as to why that's the case by looking back at panels A and B. In panel A, it's only up to X1 that the marginal benefit of the insurance policy, as incorporated in the demand curve, is greater than the marginal cost. But when type 1 drivers are charged P star, they're buying the quantity X star. For the quantities between X1 and X star, the cost of providing insurance is greater than the benefit of the insurance that's provided by exactly area G. Thus, if consumption fell from X star to X1 in the type 1 market, we would recover a deadweight loss of G. In panel B, the marginal benefit of insurance, as incorporated in the demand curve, is greater than the marginal cost all the way up to X2. But when insurance is priced at P star, type 2 consumers only buy X star. Thus, for the quantity between X star and X2, we're foregoing a surplus of F that could have been attained had consumers bought all the way up to X2. Were insurance companies able to charge separate prices for the two types of consumers, they would charge P2 for type 2 consumers and thus get consumers to buy X2, thereby recovering the deadweight loss that occurs when P star is charged. The deadweight loss arises when insurance companies cannot tell the difference between safe and unsafe drivers because they end up charging a price that's too low for unsafe drivers and too high for safe drivers. The adverse selection of unsafe drivers into the safe driver insurance pool thus causes safe drivers to buy less than the optimal level of insurance and causes unsafe drivers to buy more than the optimal level.